Hi, in this video we're going to be looking at the Fourier series of a half rectified cosine function. So this is a cosine function with just the positive parts left over, and so we will keep it generic and say it has an amplitude of x and a period of capital T. And so what we're interested in is finding the coefficients, and right off the bat we see that this is a even function. So all of our b terms are going to be 0, but we will have an a0 term because the average value is greater than 0. So 1 over t over one period. I'm going to go from minus t over 4 to t over 4. So my period is going to start there and at minus t over 4 and go to there, 3/4 t. But of course I only have to integrate up to t over 4 because it's 0 there. So straightforward integral, and I get a sine that I evaluate at t over 4 and minus t over 4, and I end up with x over pi. Alright, for the a terms, for a n terms, we have 2 over t, and again the same limits on the integral, and the same function, x cosine 2 pi little t over t, and then multiplying by our orthogonal functions, the cosines, 2 pi n t over t dt. So a little bit different here, right? This is 2 pi t over t, that's the function, and then this is our from our set of orthogonal functions, in which we vary the frequency to the harmonics with n. So how do we approach this with the product of cosines? Well, if you have the product of cosines, there's a trigonometric identity. You have a half, and then you have the sum of the two frequencies. So 2 pi t over t n plus 1, and you have the difference of the two frequencies, 2 pi t over t n minus 1. So you're going to end up with some signs again. So the 2's cancel, and then when you integrate the cosine, you pull out the stuff multiplying the t, and then sine 2 pi n plus 1 t over t. And we're evaluating that again, right? T over 4 to minus t over 4. Very similar over here, except now we have n minus 1. Okay, cool. We have to just keep doing some algebra here. The t's cancel, so 2 pi n plus 1. We have sine pi over 2 n plus 1 minus sine of minus pi over 2 n plus 1. So that's for that first term, plus now the second piece, x over 2 pi and minus 1 times sine pi over 2 and minus 1 minus sine minus pi over 2 and minus 1. Okay, so if you were on an exam or something like that, I would just sort of say you're fine to stop here after completing the integral. But we can simplify this a little bit more just for the sake of seeing that. So I'll get a new piece of paper. And the first thing in our simplification is to know that since sine is an odd function, that sine of minus x is actually equal to, minus sine of minus x is actually equal to sine of x, right? And so we can use that to combine terms that we had on the previous line, and then we have x of pi over n plus 1 times sine of pi over 2 n plus 1. So a factor of 2 disappeared, or a half, I guess. And then we have x pi n minus 1 sine pi over 2 times n minus 1. And as we often do, we say, okay, what happens as I try different values of n? And something interesting sort of happens here, right? If I put in n equals 1, I get sine of 2 times pi over 2, sine of pi. So this is actually going to go to 0. So the first term is going to be 0. My second term, I'm going to get the sine of 0 over 1 minus 1 is 0. So I have 0 over 0. And I don't know how to evaluate that. So we're going to use this thing that you maybe remember from calculus a while ago, L'Hopital's rule to evaluate. And so remember, if we have a ratio of two functions, that in the limit as the variable approaches, in this case 1, if each of them goes to 0, we take the derivative of the top and the bottom and then evaluate that limit. So what does that mean? We look at then taking the derivative of the top, which is x sine pi 2 times n minus 1, and that's going to be x cosine pi over 2 n minus 1, and then by the chain rule we get pi over 2. And then in the denominator, if we take the derivative with respect to n, so again we're taking the derivative with respect to n because that's, and we're finding the limit as n goes to 1. In the bottom we have minus pi, and so we're left with x over 2. So that's what happens when n equals 1. What about other terms? N equals 3. It turns out all the other odd terms are going to go to 0. And again, that's if we plug in, we have x of pi, sine of pi, which is just 0. So all these are going to be 0. Sine of pi, sine of 2 pi, etc. What about then n equals, the odd numbers 2, 4, 6, etc. The even numbers, well, sine of, if we just evaluate sine of pi over 2 times n plus 1, and let's evaluate sine of pi over 2 times n minus 1. So 2, we end up with sine of 3/2 pi, so that's minus 1, and sine of pi over 2, which is 1. 4, we get just the opposite, 1, minus 1, and they just do that. They just each flip back and forth. So we can say that an is going to be x over pi n plus 1 times minus 1 n divided by 2. So if n is 2, we get minus 1. If n is 4, we get minus 1 squared, so that works. And then for the other term, we get x pi n minus 1 minus minus 1 to the n over 2, because we want it to be just the opposite, right? And so we can further combine, get the same denominator on either side, combine terms, x n minus 1 times minus 1 to the n over 2 plus x n plus 1 times minus 1 n over 2 over pi, then n squared minus 1. And we end up with minus 2x minus 1 n over 2 over pi n squared minus 1. So there we go. There's our coefficients. This is a long video, but do note I think the answer in the book is wrong on this one. I think they forget this term here. But check it out and see for yourself.